Good afternoon, everyone. I am Mr. H. Thank you for joining me. In this video, we're looking here at an interdisciplinary problem involving chemistry and differential calculus. We have a specific equation written here, an equation of combustion. Hydrocarbon propane is being combusted in presence of excess oxygen. Nothing is limiting here. Everything is, in terms of this oxygen, is available in excess, and you end up producing carbon dioxide and water. This carbon dioxide is being funneled off into a flask which has a 1 liter volume. We're trying to determine the pressure of how much of that carbon dioxide will develop, and then we will talk about the change in pressure over change in time, which will be our differential calculus application. The reaction here is propane in the presence of oxygen to give carbon dioxide and water. Carbon dioxide is our point of focus for this video. You know, we're looking here at chemistry, but some of you will know this from your high school chemistry or college chemistry class. You have to start by balancing the reaction, and we can. We have 3 carbons, we'll put a 3 over here. We have 8 hydrogens, and we can put a 4 over here, and we'll get 8 hydrogens there. Now we have to balance the oxygens. On that right side, I'm seeing 6 plus 4, 10 oxygens. Here, if I put a 5, everything is balanced. Now I have to determine the amount of carbon dioxide which is produced. I'm looking here in grams. If I use that concept of moles, we know this from chemistry, it's a concept related to quantity. We can use that to determine carbon dioxide. Here's our temperature variable, here's our volume, here's our rate constant. We'll talk about that when the time comes. But let's do the chemistry part, then we'll get into the differential calculus part. I have 10 grams of propane, which has a molar mass. What's the molecular weight of this? You know, you'd have to bring out the periodic table. Carbon would be 12 times 3 plus 8. It'll be divided by 44. Just if you do this computation, you get 10 divided by 44, you get moles of propane. You have 0.22727 moles propane, which I'm abbreviating as P. And we can use this to determine the amount of this times. For this reaction, 1 mole of propane gives you 3 moles of carbon dioxide, 3 moles CO2 for each 1 mole of propane, which I'm abbreviating with a P, times 44 grams of CO2 are generated from each mole of CO2. Now look how things will cancel out. This is the factor label method. I'm cancelling out the moles P with the moles P, moles CO2 with that. If I multiply everything across, I'll get my grams of carbon dioxide, which is what I need to proceed with this question. I'll look at all of these numbers here on the top. I'll have 0.22727 times 3 times 44. That's giving me here 30 grams of carbon dioxide. But I really want to get to the n value, which, you know, if you look at these variables, you know what I'm talking about. PV is equal to nRT, the ideal gas law. Pressure times volume is equal to moles times your rate constant times your temperature. We need this now. We need N. We need moles of carbon dioxide. Moles of carbon dioxide, which is symbolized as N, is equal to grams over molecular weight. 30 divided by 44. What are you going to get? 30 divided by 44. Because that's a molecular weight of carbon dioxide. I'm getting 0.6818 moles CO2. Remember, this might be a little technical for some, but some it isn't because they've done chemistry. All of this will come into perfect sense momentarily. I've determined this. Now I know my N value for carbon dioxide, moles of carbon dioxide, because we're focusing on that, is 0.6818. We can literally erase all of this because we don't need it anymore. The purpose of this chemistry part in terms of this equation has been fulfilled. Now the situation is this. We had a little reaction chamber in which this propane was being combusted in the presence of oxygen. And you know, we're getting carbon dioxide and water, but the carbon dioxide was being funneled off here into this other chamber which had a volume here of 1 liter, as you see, 1 liter. Now what we're going to do is change the parameters, and we're going to look at the pressure of this, and we're going to see the change in pressure over change in time of this carbon dioxide as it builds up in there. The formula for the ideal gas law is PV is equal to nRT. Pressure times volume is equal to moles times your constant 0.0821 times your temperature in Kelvin. When you're looking at this in terms of pressure, the N and the T, the moles and the temperature, are directly related. As the moles or the temperature goes up, your pressure will go down. As the moles and the temperature go down, your pressure will go down. Pressure and volume are indirectly related. As one goes up, the other goes down. As one goes down, the other goes up. Now we need some other items over here. We're looking here at a change in volume over change in time as what? Minus 0.1 liters per minute. Everything here in form of minute. We're looking here at a change in temperature over change in time as what? our temperature will increase by 10 Kelvin per minute. And then we're also looking at the change in moles over change in time as 1. We're gonna increase the moles by 1 mole per minute. That's what we have over here. All of these parameters are going to come into play. We have those 3 parameters here and we have everything over here. Now bring the equation over here. PV is equal to nRT and do its derivative with respect to time. You're doing implicit differentiation of everything that you see over here. You're going to end up seeing volume and pressure here in the product rule. You'll see these in the product rule with the rate being a constant pushed outside, and watch how everything plays out. Volume times the change in pressure over change in time of the P variable plus the pressure times the change in volume over change in time of the volume variable is equal to your rate constant push outside. Because the rate is not affected by any means, no matter what, it's always 0.0821 atmospheres, liters over moles Kelvin. The unit of pressure here is in atmospheres, ATM. The unit of volume here is in liters. Moles is, as you know, in moles. Temperatures is in Kelvin. Now we look at the product rule here for the mole and the temperature. We're going to do the mole times the change in temperature over change in time of the temperature variable plus the temperature variable times the change, the moles over rate of time for that moles of the mole variable, and that's the equation over there. We have everything which falls very easily into play, but let's solve this out first. These variables here will disappear by means of the power rule. Think about them. Anything to the power of 1 will disappear by means of its derivative. You'll be left at the end with volume times change in pressure over change in time plus pressure times change in volume over change in time is equal to R times moles times change in temperature over its time plus temperature times change in moles over its time. I have every value over here listed for plugging in, and we have to find this because we're trying to calculate the change in pressure over change in time. I've calculated everything over here except for this. This I can easily calculate from this equation right here using the initial values which I had. The initial values I have are right over here. PV is equal to nRT. P is equal to nRT divided by that volume. I have N, I have R, I have T, and I have V. I have an N which is 0.6818. I calculated that at the very beginning using the factor label method from that equation, multiplied by the rate constant 0.0821 times the temperature 273 divided by 1 liters, and that tells me my pressure is 15.28 atmospheres is equal to 15.28 atmospheres. That's my value for P. I have every single value here now available to me to plug in so I can solve for this, and that's exactly what we'll do. Let's look at this. We have a volume. Volume is 1. We're looking for dP or dt. We're calculating for that. Plus, we know what our pressure is now. It's 15.28 times change in volume or change in time. It's minus. Why is it minus? Because the flask size will decrease with time. You know, as the volume will decrease, pressure builds up, the pressure will increase. I'm going to have a minus 0.1. We'll eliminate the units over here because we don't need to see them right now. If you have a rate of change which is negative, it means it's becoming less with time. If you have a rate of change which is positive, it's becoming more with time. Is equal to, look at this equation and start filling in your items. I have an R which is 0.0821. I have an N. I've calculated that N to be 0.6818 times change in temperature or change in time. My temperature will increase, meaning we're going to heat the flask also on top of that. As the temperature increases, you know, pressure increases as well because the molecules start moving faster and the pressure increases. Here we have a change in temperature of a positive 10 plus. What's my initial temperature? It's 273. What's my change in the moles over change in time? It's right here, 1 times 1. All I have here is nothing more than a simple algebraic equation for which I'm going to solve for this variable. I'm going to multiply these, add them up, and then I'll take this from that. And look what will happen. Let's start working here. I'll do 0.6818 times 10. I'm working here from within the parentheses, and I'll multiply with that, the constant, plus 273 times my rate constant 0.0821. I've done all of this. All of this is equal to 22.97. I'm going to save that value. Now I'm going to look at this. This is 15.28 times 0.1 minus 15.28 times 0.1 negative. When it goes on the other side of the equal sign, I'll add it to my saved value, which was the end result of all of this. I'll add it to that. And I'm going to get here a value 24.5 atmospheres per minute. I'm getting here dP over dt is equal to positive 24.5 atmospheres per minute. This right here is my answer to the question. What does this answer here signify? Let's talk about it. When you have an initial reaction here where propane 10 grams are being combusted in the presence of excess oxygen, and you're trying to calculate the pressure and the change in pressure over change in time for this carbon dioxide as it's collected in that flask, given the fact that you have these initial parameters and given the fact that the flask will decrease in volume over time, temperature will increase in amount over time, and the number of moles will increase over a period of time. Given all of that, you end up realizing that based on all of those parameters and the change in those parameters with this gas equation, PV is equal to nRT, the change in pressure will increase at a rate of 24.5 atmospheres per minute. The initial of this reaction is 15.28 atmospheres, but as you start affecting these variables and changing them over time, each minute you're building a pressure of 24.5 atmospheres. And this value over here will significantly increase over time by this rate. And it's a positive value which indicates it will increase over time per minute at this rate, 24.5 atmospheres. And that right there was the gist of this entire video. The question has been solved for you, and that was all I wanted to present in this video. Hopefully the chemistry part was not too technical, but you saw the procedures, and people who are familiar with the chemistry or they still remember it can easily handle those procedures. The rest of the differential calculus is as you see right here before you. And thank you for watching. Have a good day.